Assalamu alaikum dear students. I welcome you to 24th lecture of probability and stochastic processes. We have been dealing with continuous valued random variables, and starting with simple continuous valued random variables, we dealt with pair of continuous valued random variables, and then we worked with transformed random variables, those random variables which take on their values based on the values of some original random variable through a mapping or a function. In last lecture, we were working with pair of transformed random variables which assume their values based on values of two other random variables which we call underlying random variables. The value of derived random variable is obtained from values of underlying random variables through a mapping or a function, which is a mapping from two-dimensional quantity to one-dimensional quantity. And we need two such mappings. In our work, we assumed x and y to be underlying random variables which are observed as a direct consequence of the random experiment, and u and v are derived random variables which assume their values through two mappings which map values of x and y to u, and other mapping maps values of x and y to v. The two mappings that we used were u is equal to y minus x and v is equal to y plus x or x plus y. These mappings had physical significance because we were working with an example of two televisions, and x and y modeled their service time before failure. Hence u, which is y minus x, models the difference of service times of two televisions, and v, which is x plus y, models the total service time of two televisions. In last lecture, we followed a procedure where we did not assume anything about mutual independence of two derived random variables u and v. And with this assumption, we found the joint PDF of u and v. And from this joint PDF, we were trying to answer questions which involve the behavior of both underlying random variables x and y, actually both derived random variables u and v, which in turn represent the joint behavior of two underlying random variables x and y. If we had assumed that derived random variables u and v were independent, we did not have to find the joint probability of u and v. All we needed to do was that we found the individual PDF of u and individual PDF of v and multiplied the two to get the joint PDF of u and v. But we did not make any assumption about the two derived random variables u and v being independent or not. Hence, we found the joint PDF of u and v, and now we are in a position to answer questions about joint behavior of u and v, which in turn represents the joint behavior of x and y. We took the example of two television sets and we took two mappings. One was y minus x, other was x plus y. And we looked at this question, that what is the probability that the two televisions will give us a total service time of 50 months or more, and they fail each other within 6 months of each other. Please note that in last lecture, I sometime talk about the total service time of 60 months and sometime total service time of 50 months. It does not matter. All you need to do is put the right number in the processing of joint probability density functions and get the appropriate answer. I'll try to remain consistent and use total service time of 50 months. So to answer this question, we followed two approaches. In first approach, we looked at the question and looked at the constraints posed by the question and mapped that constraints to xy plane where joint PDF of x and y, two underlying random variables, is defined. And once this question was mapped on an appropriate region, all we needed to do was find the total volume of the sand hill over that region. And we found that probability of this event, that two televisions will give us a total service time of 50 months or more, and they will fail each other within 6 months, was slightly less than 1%. Actually, it was 0.00945. In the second approach, we found the joint PDF of U and V, and we found that this joint PDF was defined on two quadrants of UV plane, and it was like a V-shaped. First quadrant rotated by 45 degrees. And on this rotated joint PDF of U and V, we can define that event A, which represents that the total service time is more than 50 months, and the difference of the two service times lies from -6 to 6, or absolute value of the difference of two service times is between 0 and 6. Let's have a look at the joint PDF of U and V and see how this event is defined over the joint PDF of U and V. This shows the joint PDF. This is the V-axis and this is the U-axis. As you can see, the U-axis has positive as well as negative values because U represents the difference of two service times. So if we have taken U to be y minus x, then U can be positive or negative. But V, which is sum of two service times, is always positive, so V-axis is marked with positive numbers only. So this sloping hill is the joint PDF of U and V. And on this joint PDF, there are some constraints which came out from our question. And the first constraint is shown here with this line, and this constraint is that V is 50. And all these points to the left of this constraint represent total service time of less than 50, and all these points represent total service time of more than 50. 50 is the constraint or threshold. Now look at these two lines. These two lines are constraints about U, and this first line represents the constraint where U is 6. So all these points represent that U, the difference is more than 6, and points away from this line represents that difference is less than 6. Similarly, this line is at -6, so all points to this side of line represent the difference of two service time is greater than -6. If you combine these three constraints, then this narrow strip shown in red color is the event A, which represents that total service time is more than 50 months, and the difference of the two service times lies between -6 and +6. Please note that this strip has a width of 12 on this UV plane, but it has infinite length. It goes on and on towards positive V-axis. So you can integrate the joint PDF of U and V over this interval, and you will get your probability value for that event A. On your next slide that you can see on your screen, you can actually see how that double integral is formed. In that double integral, the limits are very simple because the outer integral is with respect to V and its limits are from 50 to infinity. Similarly, the inner integral is with respect to u and its limits are from -6 to 6. And in the integral, the integrand, the function to be integrated is joint PDF of u and v. So if you take that integrand and take this double integral appropriately, you will get your answer from integration of this joint PDF of u and v to be 0.0094, which is exactly the same as the answer we obtained by integrating the joint PDF of x and y by taking the question and mapping the constraints directly on xy plane where joint PDF of x and y was defined. Now that we have found the probability of that event using two approaches, where first we integrated a region of xy plane where joint PDF of x and y was defined, and then we integrated a selected region of uv plane where joint PDF of u and v was defined. It's proper to take a small pause, look back and observe something about the two approaches that we followed to find the probability of a certain event. When we were working with joint probability density function of x and y, we saw that this joint PDF was only defined on first quadrant, where x and y were assuming only positive values. This was true because x and y represented the service times of the two televisions, and service times are only positive quantities, the time they serve us before they fail. If you look at the UV plane where this derived random variable pair u and v was defined, then the region of UV plane where joint PDF of u and v was defined was also a 90-degree sector of the whole UV plane, but it was not parallel to the coordinate axis, it was tilted 45 degrees. So the region where FUV, the joint PDF of u and v was defined, was 45 degrees to 135 degree region of UV plane. Similarly, the region on xy plane where joint PDF of x and y was integrated was a narrow strip with orientation of 45 degrees. It was in the middle of the first quadrant where joint PDF of x and y was defined. So this strip started at 50 units from origin and then it went to infinity. When we were finding the probability of the same event on UV plane, this region, the red color region representing the event A, got also rotated by 45 degrees, and now it was running along positive V axis. It started 50 units from origin, width was 12, and then it was running towards infinity. So everything got rotated. This is not unusual. This comes from the fact that the two mappings G and H, which mapped x and y to u and x and y to v, were linear. And when we use a pair of linear transformations, then depending upon the coefficients used in those linear transformations, the region and the events rotate, scale up, get scaled down, etc., depending upon those coefficients. So if you know your linear algebra and you know how linear transformations work and how eigenvalues and eigenvectors of linear transformation play their role, you can see why a rectangular long strip got rotated and became still a rectangular long strip. I leave it up to you to recall your knowledge of linear algebra and eigenvalues, eigenvectors, rotation of basis vectors, etc., etc., to make sense out of this. Another thing that we should note is that we did not make any assumption about the independence of u and v. But can you make a guess now that you have seen how uv is defined over uv plane? It is defined over a region with this shape going all the way to infinity. A few lectures ago, actually 10-15 lectures ago, when we started our study of two random variables and their mutual independence, I gave you many hints which you could use to find if the two random variables are independent or not. One was that the region over which they are defined should be a rectangular region with sides parallel to coordinate axes. What can you say about the joint PDF of u and v by looking at the region over which it is defined? It is defined over a region which is bounded from right by the line with 45 degree slope and from the left by a line with 135 degree slope. So it's an infinite extent square kind of region. But its sides are not parallel to the coordinate axis, so this should be first hint that u and v are not independent of each other. The second hint is that when two random variables are independent of each other, they do not influence each other into taking a certain value or not taking a certain value. But in this case, u and v strictly stop each other from taking certain values. For example, if v is 50, v is sum of two service times. There can be any two positive numbers such that the sum is 50. This value of sum severely restricts the values of u, the difference that the two numbers can generate. If two numbers, both positive, give a sum of 50, can they give a difference of 200? Certainly they cannot. The maximum difference that can be generated from this sum of 50 is 50. If one number is 50, other is 0, the difference is 50. And the minimum value of difference is minus 50. If y is 0, x is 50, and 0 minus 50 is minus 50. So if v takes on a value, it strictly restricts u from taking certain values, and it forces the u to take only a certain range of values. Hence, u and v are not independent of each other, as they strongly influence each other into taking or not taking certain values. And the third way to find out if u and v are independent or not is that you take the joint PDF of u and v, find marginal PDF of u, find marginal PDF of v, multiply them together, and if the result is equal to the joint PDF of u and v, then u and v are independent. Let's do that. You can see on your screen the two marginal densities from this joint density of u and v. The first marginal density of v comes out to be 0.1 multiplied by e raised to power minus v over 20 minus e raised to power of minus v over 10. This is only one expression that is needed for marginal density of v. If we integrate the joint density in other direction, you will get the marginal density of u. And there are two expressions, one for negative values of u, one for positive values of u. And these expressions are shown on your screen, and they come out to be 1 over 30 e raised to power u over 10. That is for negative values of u. And 1 over 30 e raised to power minus u over 20, that is for positive values of u. You take any one side, either positive value of u, negative value of u, multiply it with the expression for marginal density of v, and you will quickly see that the result of multiplication is not equal to the joint density of U and V. Hence, it is clearly established that U and V are not independent of each other. Let's look at another example of two derived random variables. We are going to use the same example of two television sets, but we are going to use different mappings to get to our U and V. Actually, we are going to use the same mapping we were using for V, but for U we are going to use a new mapping. So V is again sum of the two service times. So V is x plus y or y plus x, but U is now y over x, the ratio of two service times. And if we have U and V defined in this way, then the kind of questions that we may ask is that what's the probability that sum of two service times is more than 50 months and the ratio of two service times falls between 0.5 and 2. So their service times have a maximum of 2 and minimum of 0.5. So the two televisions fail by giving service times which can at most give you a scaling of 2, ratio of 2. So with this U and V and with this question, let's try to solve this question using the two approaches we were using for the previous question. In the first approach, we'll take this question, look at its constraints and map these constraints on xy plane where original joint PDF of x and y is defined. So let's have a look at our plasma screen to see how these constraints give us our region of integration. So this is our x-axis and this is our y-axis. And this is the joint PDF, which is a sloping surface with peak at origin. So as you go away into the first quadrant along positive y-axis or along positive x-axis, this slopes down and becomes smaller and smaller. So on this sand hill, a sloping sand hill, there are three constraints. This is the first constraint, which represents the sum of two service times being equal to 50. So all these points represent those outcomes where sum of the two service times is less than 50, and all these points to the right and above of this line represents those combinations of observations of x and y which give us a total service time of more than 50 months. So this is the region we are interested in. But there are other constraints. Look at this line. This line is a line with slope of 0.5. So it is y equal to 0.5 times x. So our outcomes, our observations x and y are such that their ratio is more than that, more than 0.5. So y is equal to 0.5x here, and here y is greater than 0.5x. So all the points above this line are the points we are interested in. Similarly, this line is a line with slope 2, and all the points below this line represent our region. And if you combine all these three constraints, this is the region shown in red, which represents all those outcomes where the total service time is more than 50 months and the two service times give us a ratio which falls between 0.5 and 2. Please note the shape of this red colored region. It's a fan shaped region which starts narrow, and as you go away from origin, its width keeps increasing. So we should integrate the joint PDF of x and y over this region, which keeps on increasing its width and keeps on going till infinity to find the probability of this event B, which is that total service time should be more than 50 months and the ratio of two service times should fall between 0.5 and 2. If you want to integrate the joint PDF of x and y over this region, which is fan shaped, keeps on increasing its width, and goes along 45-degree line, you have to carefully model your double integral. When I say model, I mean you have to carefully choose the limits, and you have to carefully choose whether you are going to use vertical strips or horizontal strips. If you look at the next slide, you can see how this double integral and these strips are going to be modeled. Here, this region is shown again with three constraints. This constraint is x plus y is equal to 50. This is y is equal to x over 2, and this line is y is equal to 2x. And the region which we are going to use for integration of joint PDF x and y lies between these three constraints. And I have chosen vertical strips for initial integration, and these vertical strips are used in the integral which is inside, and on the outside the value of x is used, which goes from here all the way to infinity. But please note that as x is varying from here to here, the limiting ends of these vertical strips are bounded by this line and this line. But if you move beyond this point, then the end of this strip is bounded from below by this line and from above by the same line. So, noting this, we have to divide this double integral into two parts. First part takes integration from here to here, and the second part takes integration from here to infinity. So if you look at your slide on your screen, the exact integral is shown, and this integral has two parts, and you can clearly identify the limits from where they start, where they end, where is the internal integral, how this is along y, etc., etc. And you can find the probability of this event b, which comes out to be 0.035, slightly less than 3.5%, which is as expected because this red color region has more area than the red color region of the previous question, where it was a narrow width strip going along 45-degree line. Here the region again goes along 45-degree line, but as it moves away from a region, its width keeps on increasing, whereas in previous case it was a constant width long strip. So this was the first approach, where we looked at the question and the constraints were mapped to the xy plane, where the joint PDF of underlying random variable x and y was given, and that was integrated over the selected region to find the probability of this event b, and it came out to be slightly less than 3.5%. In our second approach to attack this problem, we are going to find the joint PDF of u and v, and we are going to process this joint PDF to find the answer of the same question, but now the question will be posed in terms of u and v. To find the joint PDF of u and v, we'll first find the joint CDF, the cumulative density function of u and v, because CDF is a family of parameterized events and their probabilities. So capital F, a function of two parameters small u and small v, is probability of event that u, the random variable, is less than small u, and v, the random variable, is less than or equal to small v. So what we are going to do is we are going to vary u and v over the appropriate range and find the probability of event FUV, which is a parameterized event parameterized by u and v, and probability of this parameterized event is the value of CDF for values of parameter used in determining the probability. And this probability determination will be on xy plane and using the joint PDF of x and y. So let's have a look at xy plane and see how varying the parameters u and v is going to affect the region of xy plane that gets used in the integration to find value of CDF for a certain pair of values of small u and small v. So this is xy plane, and this line with slope 45 represents y plus x is less than or equal to v. So this line represents the capital V, the random variable v, being less than the value of the parameter small v. So if v is very small, this line is somewhere here. If v is large, this line is here, and for still larger values, v is here. This line is here, and it crosses at v comma 0 on x-axis and 0 comma v on the y-axis. So with larger values of v, the area in this triangle, which is the area of xy plane that gets used in the integration, becomes larger and larger. This line is a line of slope u. So this is y equal to x times u, where u is the small parameter and u is also the slope of the line. So for very small slope, all the points where y is less than xu are all the points below the line with slope u, which is small. So a line with small slope is somewhere here, a line with larger slope is somewhere here, and line of still larger slope is somewhere here, and a line of infinite value of slope is vertical line. So as v increases, it takes more and more and more area of the bigger triangle defined by v. So increasing the value of parameter v, we get bigger and bigger triangle, and increasing the value of u, the slope, we take more and more portion of this bigger triangle that gets used in the integration. So as you can see, this region is the region which will be used in the integration of joint PDF of x and y to get the CDF of u and v for a certain value of u and a certain value of v. And this integration, the double integration, is modeled with horizontal strips. So inner integral will be along x and integral along y will be from 0 to this point. If you look at your slide on your screen, you can actually see the integral that is used to find the CDF. This integral is simple because it involves only one triangular area, and if you put it the value of u and v appropriately, you will find that the CDF of u and v, without making any assumptions about the independence of u and v, comes out to be u plus 2 whole into e raised to power minus v over 10 minus 2u plus 2 whole multiplied by a long complicated factor that you can see on your screen, whole divided by u plus 2. So you can see that this expression is slightly more complicated than the expression that we got for CDF of u and v for the previous example. And this complexity comes because of the mapping we used in case of u, which was y over x. But this expression is not very complicated. We can easily process it using MATLAB. And the first process that I have done to this formula is by finding the values of this CDF for a range of values of u and a range of values of v, I can sketch this two-dimensional CDF of u and v, and you can see this sketch on your screen. This is the CDF of u and v. This is where u lies, the ratio of y and x, and this is the axis where v lies, the sum of two service times. And when both are 0, the CDF is 0, and as you move away from origin, go away into the first quadrant, the value of CDF rises, and eventually it's going to become 1. So this is the general shape of the CDF, and once we have this CDF, we can differentiate it with respect to u and v, the partial derivatives, first with respect to u, then with respect to v, and we will get the PDF, the joint PDF of u and v. I have used MATLAB to find these partial derivatives, and the joint PDF is sketched on your screen. So this is the general shape of joint PDF of u and v. This is the u-axis, and only a region of 0 to 5 is used in this sketch, and this is the v-axis, sum of service time, where from 0 to 100 values are used in this sketch. And the general shape is like this, that for small values of u, as we move along v-axis, there is a hill and then it slopes away, and the height of this hill goes down as we take larger values of u. We can use this joint PDF to answer questions about the behavior of u and v, which in turn model the behavior of x and y, the two underlying random variables. And the question that we were trying to answer was that what is the probability that total service time is more than 50 months and the ratio of two service times lies between 0.5 and 2. Before we answer that question through processing of this joint PDF of u and v, let's see if we can find out if u and v are independent of each other. The first sign that we need to look for is that the region over which this joint PDF of u and v is defined should be a rectangular region with sides parallel to coordinate axes. Actually, for this case, it is true that the region for this joint PDF is again the first quadrant, because our u is ratio of two service times, which is always going to be a positive number, and the service time of two televisions added together is our other random variable, and that's also going to give you a positive number. Furthermore, if one random variable, either u or v, takes on a certain value, it does not restrict the other random variable to take on certain value or not to take on certain value. Suppose if sum of the service times is 50, then the ratio of two service times can be anything. If you want to have a small number, then y over x is the ratio of service time, then y could be 0.5 and x could be 49.5, giving you a number which is almost 0.01. You want still a smaller number, you can have x to be 0.1 and y to be 49.9. You can have any combination as long as the sum is 50 and have any ratio. You can have a very large value of ratio y over x if you take y almost equal to 50 and x very close to 0. So u and v in this case are free to take on any values, and they are defined over first quadrant, which is a rectangular region with sides parallel to coordinate axis. But does it make these random variables u and v independent? Let's look at the third clue that was discussed around 10 lectures ago, that if two random variables are independent and you have their joint PDF, and if you walk on that PDF, then the peaks are aligned. If you walk along one axis and you look at all the peaks, they should be aligned. Let's have a look at a few trajectories or walks on top of this joint PDF and see where the peaks are. And the peaks are if you move for small values of u along v-axis, so you encounter a peak and then the joint PDF dies down. Here is a collection of those trajectories along v for different values of u. And as you can see, the first peak occurs around 10, but as you move down with larger values of u, the peaks get shifted, and shifted. So by looking at the misaligned peaks, one can say that for this case, u and v are not independent of each other. But a solid proof could be obtained if we could find the marginal densities of u and v from the joint PDF of u and v and multiply them together to see if multiplication of marginal densities gives us our original joint PDF back or not. If you want to try that, you can certainly go ahead, but it's not going to work because the expression for joint PDF for this case comes out to be v into e raised to power minus 2v plus uv whole divided by 20 plus 20u. And furthermore, this whole expression is divided by 200 times u plus 1 whole square. So this joint PDF has an exponential term on top, but not a simple exponential term. The exponent has an expression of uv on top and an expression of u below. And the whole exponential term gets divided by a function which is u plus 1 whole square. So this transcendental type of function where there is one expression on top, another on bottom, is not easy to integrate. It's not possible to find closed form solutions of marginal densities of u and marginal density of v by integrating this complicated expression. Hence, for analytical proof of independence of this u and v, we cannot use our technique of marginal densities and their multiplication. By looking at the shifted peaks of the joint PDF as we move along v-axis for different values of u, we can certainly guess that for this case, u and v are not independent of each other. Now that we have found the joint PDF of u and v, and we know the region of UV plane over which this joint PDF is defined, we can certainly find answers to questions which involve joint behavior of u and v. For example, our question related to the event B that we defined is that sum of service times should be more than 50 or v should be more than 50 and ratio of two service times should be between 0.5 and 2, or u, which is ratio of service times, should lie between 0.5 and 2. So these constraints give us a region on UV plane that we should use in the integration of joint PDF of u and v to get the answer of our question. So let's see how this region looks like on UV plane. So this is the joint density of u and v, joint PDF, and this is the v-axis and that is the u-axis. So u-axis starts from here, goes this way positive, and v-axis goes this way. So this is origin. If you see at this constraint, this is where v is equal to 50, and all these points represent where v or total service time is less than 50 months, and these points represent those outcomes where total service times is more than 50 months. Look at these constraints. This constraint is where u is equal to 0.5, and if u is going to be larger than 0.5, then all these points are in our region. But the third constraint is that u, the ratio of two service times, should be less than 2. Here is u equal to 2, and all the points on this side of this line, u is equal to 2, are in our region. So this is the red colored region which is going to be used in the integration of this joint PDF of U and V to find the probability of event that total service time is more than 50 months and ratio of two service times is between 0.5 and 2. If you compare this red colored region with the red color region of XY plane, you will see marked difference. In XY plane, it was a fan-shaped region along 45-degree line with width increasing. Here, it's a rectangular strip along V-axis with U limited from 0.5 to 2. Furthermore, the region of XY plane where joint PDF of X and Y was defined was whole first quadrant, and the region over which the joint PDF of U and V is defined is also the whole quadrant. So the total region over which X and Y, Fx and Y or Fu and V is defined does not change. The total region over which the two joint densities are defined does not get rotated, but that fan-shaped region centered along 45-degree line gets rotated, becomes a narrow rectangular strip of infinite length. So this behavior is not expected. It is markedly different compared to the behavior of the first question where narrow strip got rotated 45 degrees and the whole region first quadrant also got rotated by 45 degrees. The reason is that one of the mapping U is equal to Y over X is not linear. In previous question, both of the mappings were linear, Y minus X and Y plus X. In this case, one mapping is linear, but the other mapping, Y over X, is non-linear. Hence, this is the kind of unexpected behavior of non-shifting of the total domain and rotation of the fan-shaped region and it changing its shape to become a long narrow strip. This kind of unexpected behavior is due to the non-linearity of one of the mappings. So you have identified the region on UV plane over which you must integrate the joint PDF of U and V to get the answer to that question, and it's not very difficult to do that double integral because the region is rectangular. If inner integral is with respect to U, it is always from 0.5 to 2, and if outer or external integral is with respect to V, it is from 50 to infinity. Very simple integral. You can see that on your screen. You can easily do it yourself, and if you put proper values into this double integral, the probability of this event comes out to be 0.0349 or slightly less than 3.5%, exactly equal to the probability of this event as it was found by integrating the fan-shaped region on XY plane. So what we have learned today? We learned to manipulate pair of derived random variables defined over a pair of underlying random variables. We looked at two approaches to answer questions related to derived variables which indirectly are related to behavior of the underlying random variables. We can find answers to these questions by taking appropriate area of XY plane where the underlying random variables are defined and taking the integral of the joint PDF of two underlying variables. Or we can define the same event on UV plane, which is where the joint PDF of U and V are defined. So you can find the answer to those problems using these two approaches. But the point to remember is that there are random phenomena which we observe, and then there are random phenomena which we want to investigate, and they are related through simple linear or non-linear mappings, and it is more useful to talk about the behavior of derived random variables, because that represents the quantities that we are interested in, and representing those in terms of the underlying random variables, which are the observations we directly get from the underlying random phenomena. But if you use all these techniques, all these tools, where you can either map the constraints on the underlying pair of random variables or the pair of derived random variables, or you can find the joint PDF of derived random variable from joint PDF of underlying random variables, you can get to the same answer. But the intuition you get by attacking the problem using two different approaches is very valuable, and it gives you confidence that you can work with complex, unpredictable phenomena. I end my lecture here, and in the next lecture we are going to see at procedures where instead of going through the CDF of U and V, you can find the PDF of U and V directly from the PDF of X and Y. Till then, I wish you the best. Thank you. Khuda Hafiz.